Swayam Prabha. Digital India. Educated India.
So, in the last lecture, we discussed about various types of equations of motion, primarily the Lagrangian equation of motion, which gives a second order ODE, and Hamiltonian equation of motion, which gives a two first order ODEs to update particle positions and momenta. So, now if you look at these equation of motions, whether we are talking about Lagrangian or Hamiltonian, these laws contain certain conservations. Okay, they basically conserve certain quantities. Especially we wrote these set of equations for let us say an NVE or a microcanonical ensemble. So, we know that already that this number is anyway is conserved, and then this volume and energy is also fixed. And then we want to generate trajectories by keeping this number, volume, energy constant, and if we can generate such a constant energy trajectory, we can use statistical mechanics to obtain equilibrium properties, time correlation functions. And we saw that this Lagrangian equation of motion and Hamiltonian equation of motion basically enables constant energy simulations, because we showed that the total energy given by the Hamiltonian, the time derivative is 0 along the trajectory of the system. So, now in this class we will actually see there are some other kinds of conservation that is possible in this classical equations of motion. These are so, the first one is energy conservation, which we already noted, and then we also will see that for the system the linear momentum is also conserved, and third, the angular momentum also conserved. So, what do I mean by conservation here is that these quantities remain constant throughout the simulations. So, these values energy, linear momentum, angular momentum, these depend on the initial condition that you specify for the n particle system. Once we specify that, during the system's dynamical evolution, if you take any point in that particular phase space, you will see that the energy remains constant, linear momentum remains constant, and the angular momentum also remains constant. So, now all these conservations are coming mainly because each of this conservation law underlies a symmetry. Okay. For example, if you look at this time this energy conservation law, this comes from the time symmetry or time reversal symmetry. That means, if I take the trajectory of a system, and then at any point if I just reverse the momentum of all the particles, then the system will go backward in time, tracing the initial state itself. I will talk about that a little later elaborately. And then this linear momentum comes because of translational symmetry. That means, if I move the system in space, if I translate in space, the system's property should not change, or the trajectory should not change. So, this is called translational symmetry. And then if I take the system and if I rotate about an axis, okay, to a particular orientation, then the property measured should not be also dependent on the orientation of the system. So, the rotational symmetry gives rise to the conservation of angular momentum. So, all these symmetry and the conservations pertain to the equation of motion that we talked about. The classical equation of motion that we derived based on the Hamiltonian principle, they have all these properties of time reversal symmetry, translational symmetry, and rotational symmetry. As a consequence of these three symmetry properties, you see that the quantities such as energy, linear momentum, and angular momentum are conserved in the simulations in the system. So, now the question here is the way we simulate a system in MD simulation is by not taking the entire system size pertaining to an experimental conditions, but rather taking a very small set of particles, which could be atoms or molecules. And then we already talked about how to eliminate surface effects by using periodic boundary conditions. So, so in that sense, we have a potential model which we think is correctly describing the system. Then we have a set of equation of motions which we think is having certain symmetrical properties and conservation laws. And now when we apply these models and equation of motions for a periodic system, we want to ask ourselves whether the periodic boundary condition itself is allowing the conservation of these laws or not. And we want to know what is the effect of periodic boundary conditions on these conservation laws. In fact, in one of the previous lectures, we also talked about the effect of periodic boundary conditions in certain aspects. For example, we said if there is a system which is very close to phase transition having a large length scale density fluctuations, we said that the periodic box, the edge length of the periodic box will limit the length scale of the fluctuations. So, as long as we are not very close to phase transition or critical fluctuations, so periodic boundary conditions should not have any effect. However, for a large length scale density fluctuations, this is something that we have to worry about. So, along the same line, now we are talking about the dynamical equations and how periodic boundary conditions will or will not influence the conservation principles. So, now let us talk about this time symmetry I was talking about. So, what you see in this picture is, so we have a two-dimensional space. So, we have this position q in the x axis and the momentum on the y axis, and in particular we are talking about a system which could be something like a simple harmonic oscillator. Okay, so this is basically you can think of a particle of mass m is actually bound to a spring, and then you look at the dynamics of such a simple harmonic oscillator. And then the position is given by q, and the velocity at which this particle is moving is given by q dot. Okay. So, now this is a dynamical, the system is evolving dynamically. So, that means q is a function of time, and then q dot is also function of time. So, now what we can do is from these equations you can eliminate time, and then you can have a state space relating q as a function of q dot. Okay. So, that is what is shown here. This basically tells the time is not explicitly present in this plot, but you can think of that time is implicit, and if I take a point somewhere here, this means that at time t equal to let us say 0, the position q is 0 at the origin and the momentum is plus 1. Okay. Now, you start with this initial condition that at time t equal to 0, q is 0 and p is equal to 1. So, that is our initial conditions, and then you solve the dynamical evolution of this harmonic oscillator using Hamiltonian mechanics, let us say, and then you look at different time points t1, t2, t3 etc., and then as a function of time you can see that q comes down and the p also comes down. Okay. And the direction of the trajectory motion is given by this arrow. Now, at this particular point what I can do is I can switch the sign of the momentum. So, here you can see it is a positive value. When I switch the value of momentum negative, then the momentum goes here at the same position, the q is not changed here at this point. So, we are actually arbitrarily changing the momentum by reversing the direction, and then if you look at in time the trajectory, you will see the trajectory's position will travel back to its original value, which was q equal to 0 at time t equal to 0. So, this is what we call it as a time reversible process or time reversible trajectory. So, what this basically means is if I set the momentum as minus p, the coordinates should not change, the coordinate should basically trace back its original value. So, this is one of the important property that can be shown that the classical equation of motion follows. As a consequence of this time symmetry is what I was saying as the energy being conserved. In other words, the total energy remains constant in the during the system's evolution. Now, the second aspect is effect of periodic boundary conditions on the conservation of mass, energy, linear momentum and angular momentum. So, this is something we are going to discuss now. As far as mass is concerned, this is basically the number of particles, and if you remember in the periodic boundary conditions, whenever there is a particle that moves out of the box, thereby once the particle moves out of the box, then we have the number of particles decreased by 1. But then in the periodic boundary conditions application, we also know that an image of the same particle from the neighboring box comes from the other side, so that the total number of the particle remains always constant in the system. So, inherently we see that the population the periodic boundary conditions conserves the number of particles, or in other words the mass. So, that is straightforward. The second thing is about energy conservation. So, the way we do simulation with periodic boundary conditions, whether energy is conserved or not, because of the application of periodic boundary conditions. So, in order to see that, you might have to think about a particle before it moves, and then after we apply the periodic boundary conditions to this, we know that the particle would have entered from the other side. Okay. So, we basically put the particle back in the box from the other side. So, because of this periodic image effect, we want to know whether the energy of the system changes or not. Okay. And in order to do that, so what we can do is, in this, before the particle leaves this box, we can write this energy of a particle I, which is going to leave. We will say it is an old position, and we can write this energy as half m Vi squared plus sum over j not equal to I u of Rij. So, now we have to worry about only the energy of this particle, because that is what is going to change in this particular time point. So, we do not have to worry about all the other particles. So, this particular particle has a kinetic energy given by half mv square, and then it also has a potential energy with all the neighbors within the nearest image particles. So, now after this particle is moved and then comes back from the other side, now we can write what is the energy of this system, which is INFLIBNET. We let us call it with superscript n to say this is a new position. So, when we do this, you will see that the kinetic energy remains exactly the same, because when we put the particle back, we do not alter its velocity or momentum. Okay, we only change the particle position. So, the kinetic energy remains the same. Okay, but this potential energy, that depends on Rij, the relative distance between them. And interestingly, what happens is that this Rij now should have been written as some plus or minus L, because of the periodic boundary condition is shifted by a simulation box length. And now it can be either plus or minus, because it may go in either side of the box. So, now if you remember, when we find this minimum distance between a pair of particle, we apply this minimum image conversion, so that by doing this translation, you still have the Rij unchanged. Okay. So, because of this, you see that this potential energy function, before and after you put the particle back, the energy also remains the same. So, thereby we can show that the periodic boundary condition does not change the energy of the system. Okay. So, we have shown that the number is conserved and the energy is also conserved because of the application of periodic boundary conditions. Now, the third quantity of interest is linear momentum of the system. So we define this linear momentum with a capital P. It's a vectorial quantity which is nothing but sum of I is equal to 1 to n of all the particles momentum. Okay, this is at any given time t. So if you look at this total momentum, this basically tells the total momentum of the entire system. So I might have a simulation box with many particles with respective momenta, and then we find the total linear momentum of the entire system. And now if you look at as a whole system, there is no external force acting on this this entire system itself. Okay, there is no external force. The forces are only coming because of internal intermolecular or intramolecular interactions. There is no external force acting on this system. So when there is no external force, then the rate of change of this linear momentum d by dt is given by F external. Right, this comes from again Newton's law of motion or from a Lagrangian equation of motions. So earlier we talked about writing the equation of motion for individual particles. So now we are writing for the entire system. We can define a linear momentum for the entire system and to see whether this entire system is translating in space or not, which would happen if the if there is any external force acting on the system. But we know that for an NVE simulation or NVE system, we have this external force is 0. So the time derivative of the total linear momentum is equal to 0. This basically means this linear momentum should be equal to whatever that is set at t equal to 0. That is, when you initialize the system with particle positions and momenta, you would have given certain momenta for each particle, and that gives the initial linear momentum of the entire system, and that value remains constant throughout the system's dynamical evolution. So that is called the conservation of linear momentum. Now the question is whether this property is violated or not while applying the periodic boundary conditions. I think we can easily answer that question because we know that when we apply, like I said before, when I apply the periodic boundary conditions for a particle moving from one side and entering the other side, we are changing only the particle positions and not the momenta. So that means before and after I apply this periodic boundary conditions, if I calculate the linear momentum, since P is not changed for these particles, the linear momentum also remains the same. So that means this condition is always satisfied for simulations with periodic boundary conditions. Okay, so we know that mass is conserved, energy is also conserved, and the linear momentum also conserved for this case. Now the fourth property is the conservation of angular momentum or the symmetry of rotational invariance. So the the angular momentum is denoted with this L, and it's defined as sum over all particle I is equal to 1 to n Ri cross Pi, where Ra here is the particle position and Pi is the moment of each position, and then you basically take a cross product of these two and then sum over all the particles. So that is going to give you the angular momentum. Now the question is whether this angular momentum is preserved in the simulation is something to be checked. And now again, like we said before, in the system of n particle, we have like we said no external force. Similarly, there is no external torque also acting on the system. Okay. So because of that fact that there is no external torque on the system, then the angular momentum of the system remains constant, and that is whatever is fixed at the time t equal to 0. So this L of t should be equal to L of 0 at all times. So now the question is whether periodic boundary condition affects this linear momentum or not. To see this, what we would like to do is let's find out what is the momentum before and after we apply the periodic boundary conditions. So we write this cross product as Ri x, Ri y, Ri z, or maybe for 2 dimensions I can just take it as 0. I am just considering a 2-dimensional system just for this purpose. And then the angular momentum at the new position will be I j k. So, here the R I j this one should have been changed because of the periodic box. So, you can think of R I x is something like R I x plus or minus L, and maybe R y I is also plus or minus L, and then this P I x remains the same because momentum is not touched. Okay. So, now if you ask what is the z momentum, z component of the angular momentum, from here you can see that this is basically R I x P I y minus R y y P I x. Okay. So, this is before we apply the periodic boundary conditions, and then this is the same z component of the angular momentum after applying the periodic boundary condition would be R I x plus or minus L times P I y minus R y I plus or minus L times P I x. And if you compare these two quantities, you can see that this new momentum becomes the old momentum plus or minus L times P I y and then plus or minus L times P I x, and this is the extra term that is added whenever we apply a periodic boundary conditions in the systems. So, you can see that because of this reason in the simulations the angular momentum is not conserved. So, this is something we have to keep in mind in all the simulation that we do with the periodic boundary conditions. We see this angular momentum is not conserved. That means the initial symmetry that we are talking about, that when I rotate the system about an axis to certain degrees, then the angular momentum is supposed to be conserved and the property should be invariant of rotations. But then when you actually do simulations, we are not enforcing the conservation of angular momentum, and this is something that we have to keep in mind, that if there is any property that could be a strong function of angular momentum, then we have to pay attention to means and methods of avoiding such problems. Okay. So, this is generally not discussed much in details in if you look at literature on MD simulations, but as a student of simulations, you should know that the periodic boundary condition has all these influences. It conserves some of the primary important properties like mass, energy and linear momentum, but then when it comes to angular momentum, the periodic boundary conditions violates that. How, even though we say it is violating, if you really look at how the angular momentum varies in a simulations, you will see that so what is plotted here is, as a function of time, certain component of angular momentum is plotted, and you can see that it is not constant, it is basically fluctuating about certain mean value, in this case 0. This is because in the actual simulations, there are many particles going through the box boundaries and then coming back from the other side. So, as a net effect, there seems to be certain average value of angular momentum that takes. That is why this oscillation is found. So, you can see it is not drifting away just because that means that particles are not leaving always from one side. It is basically exiting and entering from all sides. So, there is some sort of an averaging happens because of these various particles moving about, and then the angular momentum is going to show a kind of very oscillatory behavior around a mean value. Ideally, this should have been a constant value like energy, like linear momentum, but angular momentum has this particular behavior. So, now we can ask, what is the consequence of all these conservation laws being followed or not in the simulations. So, it turns out that when we try to calculate certain microscopic properties, we take care of this number of degrees of freedom as proportionality constant. Okay. And so, now when we have the conservation of these energy, linear momentum, etc., then the number of degrees of freedom will have to be changed accordingly. For example, if you consider the conservation of linear momentum, which is defined as this, so this has to be constant throughout the simulations. So this means that not all the momentum variables are independent. They also have to preserve the property that this linear momentum remains constant. Okay. So then instead of 3n momentum variable that we basically have 3n minus 3 number of degrees of freedom, because of the fact that this condition has to be satisfied. So the consequence of this would be, usually we define temperature, the microscopic temperature, as 1 by 3n kb p square by mi, right. So here this 3n is the total number of degrees of freedom that we would have used before. But now in the simulation we know that the linear momentum is conserved. So the actual temperature should have been calculated as 1 by 3 n minus 1 times kb, because the actual number of degrees of freedom is now 3 times n minus 1 rather than 3n. Okay. So because of this, you can see there is the temperature that we actually calculated with this is higher by a factor of n by n minus 1 factor. Okay. So you can see that this factor is negligible as long as n is very large. Okay. But when n is very small, maybe like 10 or 50 or 100, then this quantity can be quite significant. So this is something that we have to remember, that the influence of this number of particles in the system affecting the calculation of microscopic properties like temperature, and then as long as n is very large, we can safely ignore this correction to the number of degrees of freedom. Otherwise, we have to keep this in mind. All right, to sum up, so what we have shown here is that the classical equation of motions preserves time symmetry or time reversible symmetry, spatial symmetry, and rotational symmetry. This is because there is no external force acting on the system, so there is no change in the linear momentum of the entire system, nor there is any external force, external torque acting on the system, so as to change the angular velocity of the system. So the consequence of these symmetries gives rise to conservation of certain quantities. The time symmetry gives rise to the energy being constant. Spatial symmetry gives rise to the concept of linear momentum being constant, and the rotational symmetry gives rise to the conservation of angular momentum. So now in simulations with periodic boundary conditions, what are the things that are preserved or conserved is mass is conserved, energy is conserved, even linear momentum is also conserved, but the angular momentum is not conserved. Okay. Is not conserved. That's because of the periodic boundary conditions. So the consequence of this any linear momentum being constant during the dynamical evolution of the system also changes the number of degrees of freedom. From 3n momentum variable to 3 into n minus 1 momentum variables. Okay. So then this change in the degrees of freedom has to be properly accounted whenever you try to calculate any thermodynamic properties.